Right now, beneath your feet, Earth is keeping records you cannot see. Every major shift in chemistry, every pulse of erosion, every change in what lives and what burns gets written into layers of rock and sediment. If a technological civilization rose and fell millions of years before humans ever walked upright, the cities would be gone, the metals would corrode, and forests would erase every trace from the surface. But geology does not forget the same way surfaces do. By the end of this, you will understand exactly what traces a vanished civilization would leave in Earth's rock record, how long those traces persist, where they concentrate, and how scientists could test for them without mistaking natural events for technology. If this is the kind of science you like, subscribe for more breakdowns like this. Let's break it down, step by step. Picture a civilization that collapses today. In 100 years, roads crack and buildings crumble under roots and rain. In 1,000 years, steel bridges rust into oxide stains and concrete returns to dust. In 10,000 years, coastlines reshape, rivers shift their courses, and forests reclaim every foundation. By 100,000 years, glaciers have scraped valleys clean, and sediment has buried what remains. By 1 million years, plate tectonics begin recycling ocean floors. Volcanoes resurface continents, and mountains rise where plains once stood. The intuitive traces we think of when we imagine finding lost civilizations, ruins and walls and roads, vanish on timescales far shorter than Earth's deep past. This is the key shift in how we must think about deep time. Geology is not a museum that preserves objects. It is a recorder that preserves signals. Layers of sediment accumulate grain by grain in lakes, oceans, deltas, and basins. Ice cores trap atmospheric chemistry year by year. Marine sediments compress organic matter, ash, pollen, and dust into readable horizons. What survives is not the statue, but the chemistry it released when it corroded. Not the factory, but the isotopes it emitted when it burned fuel. Not the city, but the metals it spread into the air and the soil it eroded into rivers. This is how Earth remembers. A thin, dark layer in a rock core might record a single catastrophic decade. A shift in the ratio of carbon isotopes across 5 centimeters of sediment might encode a planet-wide change in how carbon cycled through the biosphere. A concentration of microscopic glass spheres in a marine core might mark an impact or an industrial process. These are the black box recordings geology keeps. And here is the uncomfortable question. If we are looking at the wrong kind of evidence, if we are expecting ruins when we should be searching for chemical fingerprints, if we are checking timescales too recent when the signal might lie 10 million or 50 million or 200 million years in the past, would we even notice? We are not here to prove a mystery. We are here to define what a real test looks like. We will examine 5 specific categories of traces that geology would preserve if a technological civilization existed long before us. For each trace, we will answer the same questions. What is the mechanism that creates it? Where does it accumulate? How long does it last? What natural processes could mimic it? And what measurement would decisively confirm or rule it out? The structure is simple. We start with the rules of preservation, the physics of what deep time erases and what it keeps. We define what a civilization signature actually means in measurable terms. We walk through the investigation toolkit geologists would use. Then we examine each of the 5 traces in turn. Isotopic fingerprints, technofossils and synthetic materials, artificial radionuclides, global pollutant geochemistry, and sedimentation shifts paired with biosphere footprints. We address the preservation gap, why we have not found such traces yet, and we end with a concrete search strategy, what to look for and where to look next. Every claim will be tied to evidence. Every interpretation will be separated from observation. Every alternative explanation will be stated. This is not speculation dressed as science. This is the scientific method applied to a question most people assume cannot be tested. So what does Earth actually keep when everything on the surface gets erased? Why ruins don't last? If you want to understand why we would not find skyscrapers from a civilization that existed 50 million years ago, you need to understand erosion at the scale geology operates. Water is the dominant sculptor. Rivers carve valleys. Rain dissolves limestone. Ice grinds mountains into powder. and waves batter coastlines into sand. Every exposed surface weathers. Freeze-thaw cycles crack stone. Plant roots wedge into fractures. Chemical reactions break minerals apart. On human timescales, rock seems permanent. On geologic timescales, continents are temporary. Consider the Appalachian Mountains. They formed roughly 480 million years ago during a collision of tectonic plates, and at their peak they likely rivaled the Himalayas in height. Today, after hundreds of millions of years of erosion, they are worn to gentle ridges. Entire kilometers of rock have been stripped away and carried to the sea. If mountains disappear, buildings do not stand a chance. Concrete, the material we build cities from, degrades within centuries when exposed. Steel corrodes into iron oxide within millennia. Even the most durable synthetic polymers, the plastics we assume will outlast us, break down under ultraviolet light, oxidation, and microbial action when left on the surface. The intuition that our cities will leave permanent ruins is based on timescales of decades or centuries, not millions of years. What survives is what gets buried quickly. Burial protects materials from weathering and oxidation. In river deltas, sediment accumulates fast enough to trap organic matter, pollen, charcoal, and fine particles before they decompose. In deep ocean basins far from turbulent currents, layers of sediment settle slowly and continuously, preserving a nearly unbroken record. In peat bogs, low oxygen and acidic water slow decay. In evaporate basins where ancient seas dried up, minerals crystallize and lock chemical signatures in place. Anoxic basins, regions of ocean or lake bottom with no dissolved oxygen, prevent organic material from being consumed by aerobic bacteria. This is the fundamental rule. Surface exposure erases. Burial preserves. But burial does not preserve objects the way a time capsule does. It preserves chemical and physical patterns. When a leaf falls into a lake and gets buried in sediment, the leaf itself usually rots. What remains is a carbonized film, a ghost of organic molecules, and sometimes a faint impression in the rock. When a volcanic eruption blankets a region in ash, the ash itself becomes part of the sediment record, and its chemical composition tells you what kind of magma erupted and where it came from. When forests burn and charcoal washes into rivers, the charcoal particles settle into delta sediments, creating a black layer that geologists can date and correlate across sites. Now add plate tectonics. Earth's surface is a conveyor belt. Oceanic crust forms at mid-ocean ridges, spreads outward, and subducts back into the mantle at tectonic trenches. The oldest oceanic crust still present today is roughly 200 million years old, found in the western Pacific. Everything older has been recycled. This means the ocean floor is a shredder of evidence. If a coastal civilization existed 300 million years ago, and most of its traces ended up in oceanic sediments, those sediments are gone. Continental crust is more stable. Cratons, the ancient cores of continents, can preserve rocks over 3 billion years old. Sedimentary basins on continents can hold continuous records spanning hundreds of millions of years. This is where Earth remembers best. Stable continental interiors, long-lived lake basins, cratonic marine platforms, and thick sedimentary sequences deposited in quiet environments. But even continents are not immune. Metamorphism, the process where heat and pressure transform rock, erases original textures and redistributes elements. Erosion removes entire formations. Glaciation scrapes surfaces clean. Tectonic uplift exposes old rocks to weathering. The rock record is incomplete. Geologists call these gaps unconformities, surfaces where time is missing because erosion removed what was there or deposition never occurred. Here is the picture that emerges. If you are searching for evidence of a pre-human civilization, you are not looking for intact artifacts. You are hunting for thin horizons, layers perhaps a few centimeters thick, where multiple chemical and physical anomalies cluster together in a pattern that does not match known natural processes. You are looking in the most stable archives, deep-sea sediment cores from abyssal plains, lake sediments from basins that have existed for millions of years, sedimentary sequences in cratonic basins that have remained geologically quiet, ice cores, though these only extend back roughly 800,000 years at most, and thus are useful only for very recent deep time. Peat deposits, cave formations called speleothems that grow layer by layer and trap atmospheric chemistry. Coral skeletons in some cases, though their records are shorter. The key detail is this: you are not searching for physical objects large enough to see with the naked eye, though rare microfossils of synthetic materials might exist. You are searching for patterns in chemistry, isotopes, particle distributions, and sedimentation rates. You are looking for signals that appear in multiple independent archives at the same time, because a real global event leaves a global signature. And the question narrows: what exactly would those signals look like? What counts as a civilization signature? Not all civilizations leave the same traces. A small agricultural society that farms a river valley and builds with wood and stone might leave localized shifts in pollen distributions, changes in erosion rates, and perhaps some metal tools that corrode into geochemical anomalies in soil. These are local signatures. They might show up in one lake core or one delta sequence, but they would not appear as a global signal. An industrial civilization, one that mines metals, burns fossil fuels at scale, manufactures synthetic chemicals, and reshapes landscapes with infrastructure, generates planetary signatures. Combustion releases carbon dioxide and aerosols into the atmosphere, which mix globally within months. Industrial processes create particles that settle out of the air into oceans, lakes, and ice. Large-scale mining and construction accelerate erosion, changing sedimentation patterns in rivers and deltas. Agriculture and urbanization replace diverse ecosystems with monocultures and simplified habitats, shifting the mix of pollen and species preserved in sediments. The distinction matters. A low-impact civilization, one that achieves technological sophistication without extensive fossil fuel use, large-scale mining, or industrial chemistry, might leave weaker or more localized traces. It is harder to detect. But an industrial civilization operating at a scale comparable to or greater than modern human activity would generate signals that propagate globally and embed themselves in multiple archives simultaneously. There is another key distinction. Technology itself does not guarantee a detectable trace. Impact is what matters. A society might develop advanced materials or energy systems that do not release unusual isotopes, do not produce persistent pollutants, and do not require reshaping large areas of land. Alternatively, a society might achieve only modest technology, but exploit resources so intensely that it leaves a disproportionate geochemical footprint. The question is not how advanced the civilization was by some abstract measure. The question is what physical and chemical changes it made to the planet that could survive in the rock record. This brings us to the bundle principle. One anomalous signal is ambiguous. Geology is full of strange, one-off events. A volcanic eruption can shift isotopes. An impact can scatter metals. A wildfire can deposit charcoal. A methane release can spike carbon ratios. Natural variability is high. But when 5 different types of signals cluster in the same narrow time window, in the same layer, replicated across multiple independent archives in different parts of the world, the probability that all of them are coincidental natural events drops sharply. This is the standard of evidence we are aiming for. Not one weird rock, not one unexplained isotope ratio. A package of signals that together form a pattern inconsistent with any known natural process, but consistent with industrial-scale technological activity. So, what are those 5 traces? Let us preview the logic. First, isotopic fingerprints. Large-scale combustion, chemical manufacturing, and fertilizer production can shift the ratios of carbon, nitrogen, sulfur, and oxygen isotopes in predictable ways. These shifts get recorded in marine sediments, lake sediments, ice, and organic matter. The signal is chemical. It does not require finding physical objects. Second, technofossils and synthetic materials, plastics, composite fibers, concrete-like compounds, glassy aggregates, and industrial fly ash spheres fragment into microscopic particles. These particles settle into sediments and can persist as a distinct layer. The signal is physical and chemical, detectable under a microscope and with spectroscopy. Third, artificial radionuclides. Certain isotopes, particularly those produced in nuclear reactors or weapons, are extremely unlikely to occur naturally in the ratios and distributions that human technology creates. A thin global layer containing these isotopes would be nearly impossible to explain without invoking technology. However, if the civilization never developed nuclear capabilities, this trace might not exist. Fourth, global pollutant geochemistry. Mining, smelting, refining, and combustion spread metals and rare elements into the atmosphere as aerosols. These aerosols settle globally. The key is not just elevated concentrations of a single metal, which volcanism can also produce, but unusual combinations and ratios of elements that do not co-occur in natural sources. Fifth, sedimentation shifts paired with biosphere footprints. Land clearing, agriculture, damming rivers, mining and construction change erosion rates, sediment grain sizes, and the mineral composition of sediments. Simultaneously, these activities shift ecosystems, replacing forests with grasslands or diverse habitats with monocultures. The pollen record changes, species turnover accelerates, fire regimes shift. The signal is a coupled change across sedimentology and ecology in the same horizon. Each trace has its own mechanism, its own preservation context, its own longevity, its own set of natural confounders, and its own decisive test. We will examine each in detail, but the principle is already clear. No single trace is definitive. The bundle is what matters. And here is the uncomfortable implication. If such a bundle existed in the rock record, would we recognize it? Or would we explain it away as a coincidence of natural extremes? How geologists would search the investigation toolkit. To search for evidence of a pre-human civilization, you need archives. Archives are places where Earth continuously records environmental conditions in layers that can be dated and correlated. The ideal archive has high sedimentation rates, minimal disturbance, continuous deposition over long time spans, and preservation of both physical particles and chemical signals. Marine sediment cores are the workhorses of deep-time climate and environmental reconstruction. Ships equipped with drilling rigs extract cylinders of sediment from the ocean floor. These cores can extend tens or even hundreds of meters deep, spanning millions of years. In abyssal plains far from continental margins, sedimentation rates are slow but steady, typically a few centimeters per 1,000 years. Closer to continents, on continental shelves and slopes, sedimentation is faster, providing higher resolution but sometimes more disturbance from currents and slumping. Each layer in a marine core records what settled out of the water column during that time. Clay particles, organic matter, shells of plankton, volcanic ash, cosmic dust, and any aerosols or particles that drifted globally through the atmosphere and fell into the ocean. Lake sediments offer similar records but on continents. Long-lived lakes, particularly those in tectonically stable basins, can accumulate sediment continuously for millions of years. Lake cores capture local and regional signals more strongly than marine cores, but they also receive global atmospheric fallout. Pollen grains, charcoal fragments, mineral dust, and chemical precipitates settle into lake bottoms season by season. VARVs, annual layers visible in some lake sediments, provide extraordinary time resolution, allowing geologists to resolve individual years or even seasons in the recent past. Ice cores, drilled from ice sheets in Greenland and Antarctica, trap bubbles of ancient atmosphere. These bubbles preserve the exact composition of the air, including carbon dioxide concentrations, methane levels, and trace gases. At the time the ice formed. Ice cores also capture aerosol particles, volcanic ash, cosmic dust, and any pollutants present in the atmosphere. The oldest continuous ice core records extend back roughly 800,000 years. This is far too recent to detect a civilization from tens or hundreds of millions of years ago, but it is useful for understanding what very recent industrial activity looks like in an archive and for testing detection methods. Peat bogs accumulate plant material in waterlogged, low-oxygen conditions where decay is slow. Over thousands to millions of years, peat deposits build up, preserving pollen, charcoal, and chemical signals from the atmosphere and surrounding landscape. Peat records are particularly good at capturing local land use changes and fire history. Speleothems, cave formations like stalagmites and stalactites, grow layer by layer as water drips through limestone. The water carries dissolved minerals and trace elements. As the minerals precipitate, they trap isotopic ratios of oxygen and carbon, which reflect rainfall, temperature, and vegetation above the cave. Speleothems can be dated precisely using uranium series methods and can extend back hundreds of thousands to millions of years in some cases. Coral skeletons, though more limited in time range, preserve annual growth bands and record ocean temperature, salinity, and chemistry with high resolution over timescales of decades to centuries. These are the primary archives. To search for a pre-human civilization, geologists would target the longest, most continuous, least disturbed records available. But archives alone are not enough. You need dating frameworks. Dating comes in two forms, relative and absolute. Relative dating uses the principle of superposition, the idea that in undisturbed sediments, older layers lie below younger ones. Geologists correlate layers across sites using marker horizons, distinctive layers like volcanic ash beds that can be chemically fingerprinted and matched between cores. Absolute dating assigns numerical ages. Methods include radiometric dating, which measures the decay of radioactive isotopes like carbon-14 for recent materials, uranium series isotopes for carbonates and speleothems, and argon-argon or potassium-argon dating for volcanic rocks. Other methods include magnetic polarity reversals, which provide age control by matching patterns of Earth's magnetic field reversals recorded in sediments to the known geomagnetic timescale, and orbital tuning, which aligns cyclical climate signals in sediments to known variations in Earth's orbit. Correlation across sites is critical. A real global event, like a massive volcanic eruption or an impact, leaves traces in archives around the world at the same time. A local event, like a landslide or a regional fire, appears in only one or a few nearby sites. To distinguish a planetary signal from noise, you need replication. The same anomaly must appear in marine cores from different ocean basins, in lake cores from different continents, in ice cores if they extend far enough back, and ideally in multiple types of archives. The timing must align within the uncertainty of the dating methods. What does a target horizon look like? Imagine a marine core covering the last 50 million years. Most of the core is monotonous clay and carbonate, layer after layer, with slow, gradual changes in isotope ratios reflecting long-term climate shifts. Then, within a span of perhaps 5 to 10 centimeters, which might represent 10,000 to 50,000 years depending on sedimentation rate, you find a cluster of anomalies. Carbon isotope ratios spike. Nitrogen isotope ratios shift. Concentrations of lead, copper, nickel, and rare earth elements rise sharply, and the ratios between these metals are unusual, not matching any known volcanic source. Microscopic glassy spherules appear, chemically distinct from impact spherules or volcanic glass. Charcoal abundance jumps. Pollen ratios shift abruptly from diverse forest species to a simpler mix dominated by a few types. Each anomaly alone might have a natural explanation. Together in the same narrow window, replicated in cores from the Pacific, the Atlantic, and a continental lake basin, they form a pattern. This is what geologists would search for. The replication rule is non-negotiable. One weird core is an outlier. 3 weird cores from different environments showing the same signal at the same time is a hypothesis. 10 cores is a data set worth serious investigation. So where do you start? And what would the first tests actually measure? Trace 1. Isotopic fingerprints: carbon, nitrogen, sulfur, oxygen. Isotopes are versions of the same chemical element with different numbers of neutrons in the nucleus. Carbon, for instance, occurs naturally as carbon-12 with 6 protons and 6 neutrons, and carbon-13 with 6 protons and 7 neutrons. Both are stable. The ratio of carbon-13 to carbon-12 in a sample tells you about the processes that formed it, because chemical and biological reactions preferentially use one isotope over the other. This is called isotopic fractionation. Plants, when they photosynthesize, prefer carbon-12 because it is lighter and reacts slightly faster. As a result, plant tissue has a lower ratio of carbon-13 to carbon-12 than the carbon dioxide in the atmosphere. When you burn fossil fuels, which are ancient plant material, you release carbon dioxide depleted in carbon-13. This shifts the atmospheric ratio. The same shift gets recorded in marine sediments as plankton incorporate the changed carbon dioxide into their shells and organic matter. This is not abstract theory. It is measurable. The Paleocene-Eocene thermal maximum, A rapid warming event roughly 56 million years ago is marked by a sharp negative excursion in carbon isotope ratios in marine and terrestrial sediments worldwide. The leading explanation is a massive release of methane from ocean sediments, which oxidized to carbon dioxide and shifted the carbon cycle. The signal is global, synchronous across archives, and clearly distinct from background variability. Now consider what a technological civilization would do to isotope ratios if it burned fossil fuels at industrial scale. Combustion of coal, oil, and natural gas releases carbon dioxide depleted in carbon-13, just like the natural methane release during the Paleocene-Eocene thermal maximum. But the source is different. A sustained large-scale industrial combustion event would create a sharp, negative carbon isotope excursion in a geologically brief interval. If the civilization also produced synthetic fertilizers using the Haber-Bosch process, which converts atmospheric nitrogen into ammonia, this would leave a nitrogen isotope signature, because the process does not fractionate nitrogen isotopes the same way natural biological nitrogen fixation does. Sulfur isotopes add another layer. Burning sulfur-rich coal and smelting sulfide ores release sulfur dioxide into the atmosphere, which precipitates as sulfuric acid in rain and gets incorporated into sediments. The sulfur isotope ratio depends on the source rock and the processes involved. Large-scale industrial sulfur emissions could shift sulfur isotope ratios in a pattern distinct from volcanic sulfur, because volcanoes tap mantle sources with specific isotopic compositions, while coal and ore deposits have different signatures, depending on how they formed. Oxygen isotopes in water and carbonates reflect temperature and the global ice volume. A rapid change in oxygen isotope ratios could indicate a climate shift caused by greenhouse gas emissions from industry. However, oxygen isotopes are less diagnostic of technology and more sensitive to natural climate variability, so they provide supporting context rather than a primary signal. Where do these isotopic signals accumulate? Primarily in the ocean. Carbon dioxide mixes throughout the atmosphere and dissolves into seawater. Plankton incorporate it into calcium carbonate shells and organic matter. When they die, they sink and accumulate on the seafloor. The isotopic ratios in their remains record the atmospheric and oceanic conditions at the time. This signal is global because atmospheric and oceanic mixing distributes the changed isotopes worldwide within years to decades for the atmosphere and centuries for the deep ocean. Lake sediments also capture isotopic shifts through organic matter, carbonates precipitated in the lake, and pollen. Continental peat deposits preserve plant material with carbon isotope ratios reflecting atmospheric changes. Ice cores trap atmospheric gases directly, though. As noted, their time range is limited. Longevity is strong. Once isotopic ratios are locked into carbonate minerals or organic molecules buried in sediments, they persist unless the rock undergoes metamorphism or significant diagenesis. Chemical changes during burial and compaction. In stable sedimentary basins, isotopic records can survive hundreds of millions of years. The carbon isotope excursion from the Paleocene-Eocene thermal maximum is still clearly visible in 56 million-year-old rocks. But here is where confounders arise. Volcanism can shift isotopes. Massive flood basalt eruptions, like the Siberian traps roughly 252 million years ago, released enormous volumes of carbon dioxide and sulfur dioxide, creating isotopic excursions. Methane releases from destabilized seafloor hydrates can cause carbon isotope shifts. Changes in ocean circulation, which affect how carbon cycles between surface and deep waters, can also shift ratios. Mass extinction events often coincide with isotopic anomalies because dying ecosystems and collapsing carbon cycles alter the flow of isotopes through the environment. The decisive test, therefore, is not just one isotope system showing an excursion. It is multiple isotope systems, carbon plus nitrogen plus sulfur, shifting together in a pattern more consistent with industrial processes than with any known natural event. The timing must be synchronous across multiple independent archives. The magnitude and direction of the shifts must match what large-scale combustion and industrial chemistry would produce. And ideally, the isotopic excursion would coincide with other traces, technofossils, metals, or sedimentation changes, forming a bundle. Let us walk through a scenario. Imagine geologists analyzing a marine sediment core from the deep Pacific, covering the interval from 80 to 60 million years ago. Most of the core shows stable carbon isotope ratios fluctuating gently with natural climate cycles. Then, within a 10-centimeter interval dating to roughly 70 million years ago, the carbon isotope ratio drops sharply, indicating a massive input of isotopically light carbon. Nitrogen isotopes shift in a direction inconsistent with natural denitrification, but consistent with synthetic ammonia production. Sulfur isotopes show a spike with a ratio that does not match the known volcanic activity from that time. Alone, this could be a coincidence. Maybe a methane release happened to overlap with an unusual volcanic eruption and some unrelated biological shift. But now add replication. Cores from the Atlantic and Indian Oceans show the same signals in sediments of the same age. A lake core from a stable basin in Central Asia shows the carbon and nitrogen shifts in its organic matter. A peat deposit from South America shows the carbon excursion in fossil leaves. At this point, the hypothesis that this is a natural coincidence becomes strained. The alternative, that a process acted globally and simultaneously in a way that shifted multiple isotope systems together, becomes harder to dismiss. If that process is inconsistent with known volcanism impacts or methane releases, the question of what caused it becomes urgent. This is the power of isotopic fingerprints. They do not require finding objects. They are measurements, numbers, ratios that can be compared across samples and across time. They are among the most robust traces a civilization could leave, because they encode the chemistry of planetary scale activity directly into the rock record. And yet, the question remains, would such a signal stand out clearly enough, or would it be subtle enough to blend into the noise of natural variability? Trace 2. Technofossils and synthetic materials. When we think about artifacts, we think about intact objects, a pottery shard, a metal blade, a glass bottle. But on geologic timescales, intact objects almost never survive unless they are buried quickly in exceptional conditions. What does survive in some cases are fragments so small that they behave like sediment particles and chemical residues that persist even when the original structure has disintegrated. Plastics are the most familiar example. Modern human civilization produces hundreds of millions of tons of plastic every year. Much of it fragments into microplastics, particles smaller than 5 millimeters, through weathering, abrasion, and UV breakdown. These microplastics enter rivers, oceans, and soils. They settle into sediments, and because many synthetic polymers are chemically stable in anoxic buried conditions, they can persist for thousands to potentially millions of years. Under a microscope, microplastics are recognizable by their morphology. They have sharp edges, smooth surfaces, or fibrous structures inconsistent with natural mineral grains or organic fragments. Spectroscopic analysis, techniques like Fourier transform infrared spectroscopy or Raman spectroscopy, can identify the chemical structure of the polymer, confirming it is synthetic. If a pre-human civilization used polymer-based materials at industrial scale, fragments would accumulate in sediments globally. The mechanism is simple. Plastics break down into smaller and smaller pieces. Rivers carry them to deltas and continental shelves. Atmospheric transport disperses microfibers. Ocean currents distribute particles to deep-sea settling zones. Over time, a thin layer enriched in synthetic polymer fragments would form in sediments deposited during the civilization's existence. Where would this accumulate most densely? River deltas, where sediment loads are high and deposition rates are fast, would capture particles washing out of watersheds. Continental shelves, the shallow submerged margins of continents, receive heavy sediment input and are less prone to erosion than deeper slopes. Deep-sea fans, areas where sediment flows down submarine canyons and spreads across the abyssal plain, would also trap particles. Lake bottoms, particularly in large, long-lived lakes, would accumulate microplastics from their drainage basins. Longevity depends on the environment. In oxic conditions with oxygen and microbial activity, some plastics degrade over centuries to millennia. Polyethylene and polypropylene are relatively resistant. PET, used in bottles, can break down faster. In anoxic conditions, buried in sediments without oxygen, degradation slows dramatically. Some polymers might persist for millions of years, though they would likely alter chemically, losing plasticizers and becoming more brittle. What might remain as a chemical ghost, detectable through spectroscopy, or a morphological trace, oddly shaped particles that do not fit natural categories. But plastics are not the only candidates. Composite materials, fibers made from carbon, glass, or ceramics embedded in polymer matrices, fragment into microscopic shards. Concrete, or more precisely concrete-like technogenic minerals, form when cement reacts with aggregates. If a civilization used cement at large scale, particles of calcium silicate hydrates, the binding phase of concrete, might appear in sediments near construction sites. Over time, these particles could be transported and deposited more widely, especially if rivers eroded urbanized areas. Another candidate is glassy aggregates. High-temperature industrial processes like metal smelting, coal combustion, and waste incineration produce slag and fly ash. Fly ash consists of microscopic glassy spheres formed when molten droplets of silicate and metal oxides cool rapidly in the air. These spherules are chemically distinct from natural volcanic glass because they form at different temperatures and from different source materials. Industrial fly ash spheres contain unusual combinations of aluminum, silicon, iron, calcium, and trace metals in ratios that do not match magma compositions. In a sediment core, a sudden appearance of glassy spherules with industrial-like chemistry would be striking. Natural volcanic eruptions also produce glass, but volcanic glass has diagnostic compositions tied to specific magma types: basaltic, andesitic, rhyolitic, each with known ranges of element ratios. Fly ash from coal combustion, for instance, has higher concentrations of certain trace elements like arsenic, selenium, and rare earth elements in patterns reflecting the coal source, not mantle or crustal magma. Confounders exist. Natural hydrocarbons, the precursors to fossil fuels, can form waxy or resinous substances that might be mistaken for degraded plastics if only visual morphology is used. However, spectroscopy would distinguish them. Volcanic glass can form spherules, but their chemistry points to magmatic processes. Wildfire produces charcoal and soot, which can be abundant in sediments, but charcoal has a distinct structure under magnification and lacks the chemical signatures of synthetic polymers or industrial slag. Impact events create glass spherules, called microtectites, but these have characteristic compositions, often enriched in silica and showing shock features, and they are typically found in thin global layers associated with known impact craters or structures. The decisive test is a combination of particle morphology, chemical composition, and distribution. If microscopic particles in a sediment layer have morphologies inconsistent with natural processes, if spectroscopy reveals synthetic polymers or industrial chemistry fingerprints, if the particles appear in a narrow stratigraphic horizon replicated across multiple sites globally, and if their chemistry does not match volcanic, impact, or hydrocarbon sources, the interpretation becomes difficult to avoid. A mini-case comparison helps. The Anthropocene, the proposed epoch marking human impact on Earth, is characterized in part by a global microplastic layer. Studies of sediment cores from lakes, estuaries, and deep ocean basins show that microplastic abundance rises sharply in sediments deposited after roughly 1950, coinciding with the mass production of plastics. This is a clear marker horizon. It is geologically instantaneous, appearing worldwide within decades. It is chemically distinct, identifiable with spectroscopy. And it is coupled with other signals: radionuclide fallout from nuclear tests and shifts in carbon isotopes from fossil fuel burning. If a pre-human civilization left a similar signature, the microplastic equivalent would appear as a thin layer in sediments deposited during their industrial phase. The layer might be only a few centimeters thick, representing a few thousand to tens of thousands of years depending on sedimentation rate. Above and below, sediments would show no such particles. The contrast would be stark. But there is a subtlety. If the civilization collapsed and surface plastics degraded over millions of years before being buried, the signal might weaken or become more diffuse. This is where burial speed matters. River deltas and continental shelves with high sedimentation rates would capture and preserve particles more effectively than deep abyssal plains with slow deposition. Another subtlety is dilution. A small, localized civilization might produce technofossils that appear only in specific basins or coastal areas. A planetary-scale industrial civilization, operating on multiple continents with global trade and transportation, would disperse particles more widely, creating a detectable global layer. The longevity question is open. We do not have direct experiments showing how microplastics behave over millions of years in burial. Polymer chemistry suggests that in anoxic, cool, stable conditions, some plastics could survive largely intact. In warmer or more chemically active environments, they would degrade into smaller molecular fragments, possibly leaving only residues detectable with advanced analytical techniques. But even residues are traces. Even a chemical signature is data. Here is the key takeaway. Technofossils shift the search from looking for large, intact artifacts to looking for microscopic particles and chemical patterns. It is a change in scale, but not in principle. Geology already does this. Micropaleontology identifies species from tiny shells. Palynology reconstructs ecosystems from pollen grains. Geochemistry analyzes parts per million concentrations of elements. The tools exist. The question is whether anyone is looking for the right particles in the right layers. What would make the signal unmistakable, and what could still leave it ambiguous? Trace 3. Artificial radionuclides, the barcode trace. Some isotopes are so unlikely to occur naturally in specific combinations and distributions that their presence would be nearly diagnostic of technology. These are artificial radionuclides, isotopes produced in nuclear reactors, particle accelerators, or nuclear explosions which either do not exist in nature or exist only in trace amounts from rare cosmic ray interactions or decay of natural radioactive elements. The mechanism is straightforward. Nuclear fission, the splitting of heavy atomic nuclei like uranium-235, produces a suite of daughter isotopes, the fission products. These include isotopes like cesium-137, strontium-90, iodine-129, and technetium-99, among others. Some of these isotopes have half-lives ranging from years to millions of years. Nuclear fusion, the process in hydrogen bombs or potential fusion reactors, can produce tritium, hydrogen-3, and other light isotopes. Neutron activation in reactors creates isotopes like cobalt-60 and europium-154. The key is not just the presence of a single isotope, but the pattern. A natural process, like the spontaneous fission of uranium or the decay of thorium, produces radionuclides in very specific ratios determined by nuclear physics. Cosmic rays striking the atmosphere can produce isotopes like carbon-14, beryllium-10, and chlorine-36, but again in predictable ratios and at low concentrations. A nuclear reactor or a nuclear explosion produces a different mix, a fingerprint of isotopes that does not match natural sources. For example, plutonium-239 does not occur naturally on Earth in detectable amounts because its half-life is roughly 24,000 years, and any primordial plutonium present when Earth formed has long since decayed. The only way to produce it is through neutron capture in uranium-238, which happens in reactors or during nuclear explosions. Finding plutonium-239 in sediments, especially in a thin global layer, would be extraordinary. Similarly, the ratio of cesium-137 to strontium-90 is characteristic of fission events. Both isotopes are fission products, but their yields depend on the fissioning isotope and the neutron energy. Natural uranium fission and reactor fission produce different ratios. If a sediment layer contained both isotopes in ratios inconsistent with natural spontaneous fission, but consistent with high-energy fission, the implication would be clear. Where do artificial radionuclides accumulate? Primarily through atmospheric deposition. Nuclear explosions inject radioactive particles into the stratosphere, where they circulate globally and settle out over months to years. This creates a thin, synchronous layer in sediments worldwide. Ice cores from Greenland and Antarctica show clear fallout layers from atmospheric nuclear tests in the 1950s and 60s. Marine sediment cores and lake cores also capture this signal. The layer is geologically instantaneous, a marker horizon that can be dated precisely and correlated across archives. If a pre-human civilization conducted nuclear tests or had reactor accidents that released radionuclides into the atmosphere, a similar global layer would form. The isotopes would decay over time, but those with longer half-lives would remain detectable for millions of years, depending on the sensitivity of measurement techniques. Longevity varies by isotope. Tritium, with a half-life of roughly 12 years, decays to undetectable levels within a century. Cesium-137 half-life roughly 30 years, becomes difficult to detect after a few centuries to a millennium. Strontium-90, half-life roughly 29 years, similar. But iodine-129, half-life roughly 16 million years, persists. Technetium-99, half-life roughly 213,000 years, persists. Plutonium-239, as mentioned, has a half-life of roughly 24,000 years, but isotopes like plutonium-244, if produced, have half-lives in the tens of millions of years. The challenge is detection sensitivity. After millions of years, even long-lived isotopes decay to extremely low concentrations. Advanced mass spectrometry techniques, like accelerator mass spectrometry, can detect isotopes at part per trillion levels or lower, but background noise from cosmic rays and natural radioactivity sets a floor. The question is whether enough isotopes would remain above that floor to be distinguishable. However, if the civilization used nuclear technology extensively, producing large amounts of long-lived isotopes and distributing them globally, the integrated signal could be strong enough to persist detectably even after tens of millions of years. The combination of multiple isotopes, each with different half-lives, would create a distinctive decay pattern, a barcode that could be modeled and compared to observations. Now the confounders. Natural radioactivity from uranium, thorium, and potassium is ubiquitous, but these isotopes and their decay products have well-known abundances and ratios. Spontaneous fission of uranium-238 occurs, but at extremely low rates, producing fission products in tiny quantities. Cosmic ray interactions produce isotopes like beryllium-10, aluminum-26, and chlorine-36, but the production rates and ratios are well modeled. A truly unusual confounder would be a natural nuclear reactor, like the Oklo reactors in Gabon, which operated roughly 2 billion years ago when uranium concentrations and isotopic ratios were different. But Oklo is a unique case, and its isotopic signatures are localized, not global. No known natural process creates a thin, globally distributed layer of fission products in ratios inconsistent with cosmic ray or spontaneous fission sources. Another potential confounder is a supernova, or other astrophysical event depositing radioactive isotopes on Earth. Supernovae produce a wide range of isotopes through nucleosynthesis. If a nearby supernova exploded and its ejecta reached Earth, it could create a layer enriched in certain radionuclides. However, the isotopic mix would differ from fission products, leaning toward heavier elements formed in stellar processes, and the event would likely leave other signatures like an iridium anomaly similar to impact layers or a spike in cosmic ray. Markers. The decisive test is specificity. A combination of isotopes like plutonium-239, technetium-99, iodine-129, and fission product isotopes in ratios matching reactor or weapon signatures appearing in a thin global layer replicated across multiple independent archives with timing consistent across sites would be nearly impossible to explain naturally. But there is a critical limitation. If the pre-human civilization never developed nuclear technology, this trace would not exist. Nuclear capability is not a necessary feature of all technological civilizations. A society could reach high industrial capacity using renewable energy, hydropower, or other means without ever splitting the atom. In that case, the radionuclide signature would be absent, and its absence would tell you nothing about whether the civilization existed. This is why the bundle principle matters. Radionuclides are one potential trace, perhaps the cleanest barcode if present, but not the only test. If other traces, isotopic shifts, technofossils, metals, sedimentation changes, all cluster in the same horizon but no radionuclides appear, the interpretation would be a civilization without nuclear technology. If radionuclides appear alongside other traces, the case becomes overwhelming. A mini-case comparison helps again. The Anthropocene marker includes a global plutonium layer from atmospheric nuclear testing, cores from lakes, peat bogs, ice sheets, and ocean sediments show a sharp rise in plutonium-239 concentrations starting in the 1950s, peaking in the early 1960s, and declining after the partial test ban. Treaty in 1963. This layer is geologically instantaneous, globally synchronous, and chemically diagnostic. It is one of the clearest markers that human industrial activity left in the rock record. If a similar layer appeared in sediments dated to 70 million years ago, it would not be dismissed easily. The first reaction would be skepticism, checking for contamination, verifying the dating, and replicating the measurement in other cores. But if replication held, if independent labs confirmed the isotopes, if the timing aligned across archives, the hypothesis space would narrow sharply. Here is the uncomfortable thought. If such a layer exists and is far enough back in time that the shorter-lived isotopes have decayed completely, leaving only the long-lived ones, and if those long-lived isotopes are at the edge of detection limits, the signal might be overlooked or attributed to background noise. Alternatively, if the layer is present but researchers have not sampled the right depth interval in the right cores, it could remain undiscovered simply because no one was looking for it. The question becomes, where should we look? And how sensitive do the measurements need to be? Trace 4. Global pollutant, geochemistry, metals, element ratios, persistent organics. When humans mine, smelt, refine, and burn materials, they redistribute elements across the planet. Lead from ore deposits gets smelted and dispersed as aerosols. Copper from mines ends up in wires, pipes, and products that corrode and release particles. Rare earth elements, concentrated for electronics and magnets, enter waste streams. Coal combustion releases trace metals like mercury, arsenic, selenium, and vanadium. These metals settle out of the atmosphere into soils, lakes, oceans, and ice. The signal is not just that metal concentrations rise. Natural processes can also mobilize metals. Volcanism releases metals from magma. Weathering of metal-rich rocks can elevate concentrations in river sediments. Hydrothermal vents on the ocean floor spew metal-rich fluids. The signal that distinguishes industrial activity is the pattern of elements, the combinations and ratios that do not match natural sources. For example, lead has 4 stable isotopes: lead-204, lead-206, lead-207, and lead-208. The ratios between these isotopes vary depending on the source rock because lead-206 and lead-207 are produced by radioactive decay of uranium, and lead-208 is produced by decay of thorium. Ore deposits have characteristic lead isotope ratios reflecting their age and formation environment. When lead from a specific ore deposit is smelted and dispersed, the aerosols carry that isotopic signature. Studies of Arctic ice cores and lake sediments show that lead pollution from ancient Roman and medieval European smelting left isotopic fingerprints distinct from local natural lead. Modern gasoline additives used tetraethyl lead from specific ore bodies, and the isotopic signature of that lead appears in sediments globally during the mid-20th century. This is a diagnostic trace. It is not just elevated lead. It is lead with an isotopic ratio pointing to a specific anthropogenic source. Extending this principle, a pre-human industrial civilization that mined and processed ores would leave similar signatures. The key is finding element combinations and isotopic ratios that do not co-occur naturally. For instance, simultaneous enrichment of lead, copper, zinc, nickel, chromium, and rare earth elements in ratios inconsistent with volcanic emissions, hydrothermal fluids, or crustal weathering would be striking. If the isotopic ratios of lead or other elements like strontium or neodymium point to ore deposits rather than igneous or sedimentary natural processes, the case strengthens. Where do these pollutants accumulate? Atmospheric aerosols disperse globally within weeks to months, depending on the altitude they reach. Particles settle out in precipitation, dry deposition, and eventually into surface waters. Ice sheets and glaciers capture atmospheric fallout directly, preserving a record of metal concentrations and isotope ratios over time. Lake sediments, particularly in remote areas far from local metal sources, record global atmospheric deposition. Marine sediments capture both atmospheric fallout and riverine input. Floodplains and alluvial deposits downstream of mining or industrial sites might show more localized but intense metal enrichment. Longevity depends on the element and the environment. Metals like lead, copper, and zinc are chemically stable in most sedimentary conditions and persist for hundreds of millions of years. They can be remobilized if sediments undergo oxidation or acidification, but in anoxic, reducing conditions, they remain locked in sulfides and carbonates. Rare earth elements are relatively immobile once incorporated into sediments. Organic pollutants, like polycyclic aromatic hydrocarbons from combustion or persistent synthetic chemicals, can degrade over time, especially in oxic conditions, but some residues may persist as molecular fossils or adsorbed onto clay particles. The confounders are real. Volcanic eruptions emit metals. The Deccan Traps, massive flood basalts that erupted roughly 66 million years ago, released enormous quantities of sulfur, mercury, and other trace metals, which appear as enrichments in sediments of that age. However, volcanic emissions have diagnostic isotopic and elemental fingerprints. Magmas from the mantle have specific ratios of elements like niobium to tantalum, or ratios of incompatible trace elements that reflect their source. Industrial emissions derived from crustal ore deposits have different ratios. Impact events can also scatter metals. The Chicxulub impact, roughly 66 million years ago, deposited a global layer enriched in iridium, a metal rare in Earth's crust but more common in meteorites. Other siderophile elements, those that prefer metal phases, are also enriched in the impact layer. But the combination is characteristic of extraterrestrial material, not industrial processing. Hydrothermal activity on the seafloor deposits metal-rich sediments in specific locations, near mid-ocean ridges and volcanic arcs. These deposits are localized, not global, and their chemistry reflects the fluids and source rocks involved. The decisive test is again the bundle. If a thin sedimentary horizon shows simultaneous enrichment in multiple metals, with isotopic ratios pointing to crustal ore sources rather than mantle or meteoritic sources, with element combinations inconsistent with volcanism or impacts, and with replication across multiple independent archives globally, the explanation space narrows. If this metal signature coincides with isotopic shifts in carbon and nitrogen, with technofossils, and with sedimentation changes, the coincidence becomes implausible as a natural event. Let us consider a scenario. A marine sediment core from the North Atlantic, covering the interval from 100 to 80 million years ago, shows a 10-centimeter layer where lead concentrations spike by a factor of 5. Isotopic analysis reveals that the lead has ratios matching ore deposits in cratonic crust, not mid-ocean ridge basalts. Copper and zinc concentrations also rise, in ratios inconsistent with known volcanic eruptions from that time. Rare earth elements are enriched, but their distribution pattern, the relative abundances of light versus heavy rare earths, does not match typical crustal weathering or hydrothermal input. Mercury concentrations spike, but the isotopic fractionation of mercury does not match volcanic emissions. This same pattern appears in cores from the South Pacific and the Indian Ocean, in sediments of the same age. A lake core from a cratonic basin in Africa shows the metal enrichments in its sediments. The timing aligns within dating uncertainties. Natural explanations would struggle. No known volcanic eruption produces this combination of metals with these isotopic signatures across multiple ocean basins simultaneously. No impact event leaves a signature like this. Hydrothermal sources are too localized. The alternative is a process that mined and processed ores on a planetary scale, dispersing the byproducts globally through the atmosphere. Persistent organic pollutants add another dimension. Industrial chemistry produces compounds that do not occur naturally, or occur only in trace amounts from abiotic synthesis. Examples include certain chlorinated hydrocarbons, polychlorinated biphenyls, and specific polycyclic aromatic hydrocarbons, with structures indicative of high-temperature combustion rather than natural fires. These compounds can adsorb onto particles and settle into sediments. Over millions of years, many would degrade, but some molecular structures are remarkably stable, especially in anoxic sediments. Even degradation products, specific patterns of breakdown can be diagnostic. Natural organic matter is complex, but it follows patterns. Plant waxes, lignins, and other biological molecules have characteristic structures. Petroleum hydrocarbons, formed from ancient organic matter, have specific distributions of compounds. Combustion of wood or fossil fuels produces polycyclic aromatic hydrocarbons, but the relative abundances of different compounds depend on the source and combustion temperature. High-temperature industrial combustion produces a different fingerprint than low-temperature wildfires. A global layer showing unusual organic compounds or unusual ratios of known compounds in sediments replicated across sites would add to the pollutant geochemistry case. This is more challenging to interpret than metals because organic chemistry is variable and preservation is less certain, but it is not impossible. The integrated picture is this. Metals and element ratios are among the most robust geochemical traces a civilization could leave. They are measurable with well-established techniques. They persist in the rock record for hundreds of millions of years. They can be isotopically fingerprinted to distinguish sources, and when combined with other traces, they form part of the bundle that makes a natural explanation increasingly untenable. But again, the question is scale and sensitivity. A small civilization might leave metal signatures only locally. A planetary-scale industrial society would disperse metals globally. The detection threshold depends on how much was emitted, how widely it dispersed, and how fast sediments buried it. How many independent archives would need to show the signal before the hypothesis becomes unavoidable? Trace. 5. Sedimentation shifts plus biosphere footprint. The largest scale signature a civilization might leave is not a chemical anomaly but a physical and biological restructuring of landscapes. Land clearing for agriculture removes forests and replaces them with crops. Construction and mining move vast quantities of soil and rock. Dams alter river flows. Urbanization paves over ecosystems. All of this changes how sediment moves across the planet and what kinds of organisms live where. The sediment signal is measurable. When forests are cleared, erosion rates increase. Soils that were held in place by root systems wash into rivers during rains. Rivers carry higher sediment loads. Deltas grow faster. Continental shelves receive pulses of fine sediment. The grain size distribution in sediments changes because faster erosion delivers more clay and silt relative to sand. The mineral composition shifts because different source rocks are exposed and eroded. Geologists measure sedimentation rates by analyzing sediment cores and calculating how much material accumulated per unit time. A sudden increase in sedimentation rate, appearing in multiple river deltas and coastal basins simultaneously, would indicate a planet-wide change in erosion. Natural causes include climate shifts like glaciations or deglaciation, which expose new landscapes to erosion, or tectonic uplift, which steepens slopes and accelerates erosion. But these processes operate over millions of years, not thousands. An industrial civilization, even without modern machinery, could accelerate erosion dramatically within centuries to millennia through deforestation, agriculture, overgrazing, and construction. The sediment pulse would appear as a distinct layer in cores, thicker than expected for the time interval, with grain sizes and mineral compositions reflecting the exposed source rocks. Where does this accumulate? River deltas, estuaries, continental shelves, lake bottoms, and alluvial plains. The distribution would not be uniform. Regions with intensive land use would show stronger signals. But if the civilization operated on multiple continents, the signal would appear in multiple basins globally. Longevity is excellent. Once sediment is deposited and buried, it becomes part of the rock record. The layer persists until erosion removes it or tectonic processes recycle it, which can take hundreds of millions of years in stable basins. Now add the fire signal. Large-scale combustion, whether from clearing forests, burning fuel, or industrial processes, produces charcoal and black carbon. These particles are chemically stable and accumulate in sediments. Natural wildfires also produce charcoal, so the key is distinguishing industrial-scale burning from natural fire regimes. Natural fire frequency depends on climate, vegetation, and ignition sources like lightning. Charcoal abundance in sediments varies with these factors, but it follows patterns. A sudden spike in charcoal, especially if accompanied by a shift in charcoal particle morphology or chemistry, could indicate a change in fire regime. High-temperature combustion produces different charcoal structures than low-temperature smoldering fires. Industrial combustion of coal or oil produces specific types of soot particles with particular chemical signatures. A global charcoal layer, synchronous across sites with particle characteristics suggesting high-temperature combustion, would be notable. If this layer coincides with the sedimentation pulse, the erosion and fire signals reinforce each other. The biosphere footprint adds the final dimension. Ecosystems respond to disturbance. When forests are cleared for agriculture, the pollen record changes. Sediments shift from high diversity of tree pollen to dominance by grasses, crops, or weedy pioneer species. If the civilization domesticated plants or animals, the pollen and faunal remains would show these species appearing in new locations or increasing dramatically. Species turnover accelerates when habitats are simplified. Generalist species thrive. Specialists decline. Invasive species, transported deliberately or accidentally by trade and travel, appear in regions where they did not exist before. The fossil record in sediments captures this. Pollen, plant macrofossils, insect remains, small mammal bones, fish scales, and shells all preserve ecological shifts. A striking pattern would be a simultaneous shift in multiple ecosystems globally. Forests in different regions show the same transition to grassland or agricultural landscapes. Lakes in separate continents show appearance of the same introduced species. This is inconsistent with natural climate shifts, which affect ecosystems differently depending on latitude, altitude, and local conditions. Confounders are significant. Climate change drives major ecological shifts. The transition from the Pleistocene to the Holocene, roughly 11,700 years ago, saw dramatic changes in vegetation, animal distributions, and fire regimes as ice sheets retreated and climates warmed. Glaciations expose and submerge continental shelves, changing sea levels and sediment delivery to oceans. Volcanic eruptions can cause regional to global cooling, altering ecosystems and sedimentation. The decisive test is the coupling. A natural climate shift might increase erosion in some regions while decreasing it in others. A natural fire regime change might spike charcoal in one area but not globally. A natural ecological transition might shift pollen composition gradually over thousands to tens of thousands of years. But a coupled signal, simultaneous increases in sedimentation rate, charcoal abundance, and ecosystem simplification across multiple continents, all within a geologically brief interval, is harder to attribute to climate alone. If this coupled signal coincides with isotopic shifts, metal enrichments, and technofossils in the same narrow horizon, the bundle becomes compelling. Let us construct a scenario. Sediment cores from the Amazon Delta, the Mississippi Delta, the Nile Delta, and the Ganges Delta all show a layer where sedimentation rate doubles over a span of roughly 5,000 years. Grain sizes shift toward finer material. Charcoal abundance spikes. Pollen records shift from diverse tropical and temperate forests to grass-dominated assemblages with high proportions of a few species. Lake cores from Central Africa, North America, and Asia show similar pollen shifts and charcoal spikes in sediments of the same age. Dating places these events roughly 90 million years ago, well before any known natural climate event that could explain such a global, synchronous shift. Carbon and nitrogen isotopes in the same layers show excursions consistent with large-scale combustion and fertilizer use. Metal concentrations rise with isotopic signatures pointing to ore processing. Microplastic-like particles appear in the sediments, chemically distinct from natural polymers. At this point, the hypothesis that this is all coincidental natural variability collapses under the weight of improbability. The alternative, a planetary-scale process reshaping landscapes, burning vegetation, eroding soils, and altering ecosystems, becomes the simpler explanation. And if that process does not match any known natural mechanism, the question of agency becomes unavoidable. The sedimentation and biosphere signal is powerful because it integrates multiple lines of evidence. Sedimentology, palynology, charcoal analysis, geochemistry, and paleontology all contribute. The signal is not subtle. It is a major restructuring of how Earth's surface processes operate. And it persists as a readable record in sedimentary basins for hundreds of millions of years. But here is the final twist. A civilization could be advanced and low impact if they used sustainable agriculture, renewable energy, minimal mining, and careful land management. The sedimentation and biosphere signal might be weak or localized. In that case, this trace would not be global, and its absence would not rule out the civilization. It would only indicate that the civilization did not reshape landscapes at industrial scale. This brings us back to the central point. No single trace is definitive. The bundle is what matters, and the bundle must be tested, measured, replicated, and compared against every plausible natural alternative before any conclusion is drawn. What remains is to address why, if such a bundle could exist, we have not found it yet, and what that absence tells us. Why haven't we found it? The preservation gap. If a technological civilization existed tens or hundreds of millions of years ago and left the traces we have described, why have geologists not reported finding them? There are several answers, and they constrain the scenarios without eliminating them. First, ocean crust recycling removes evidence. Roughly 60% of Earth's surface is ocean floor. The oldest oceanic crust still present is roughly 200 million years old. Everything older has been subducted into the mantle and melted. If a civilization existed 300 million years ago and most of its activity occurred on or near coastlines, which is plausible since coasts offer access to resources and trade, much of the sedimentary record of that civilization might now be gone. Only traces preserved in continental sediments or deep sea sediments that later accreted onto continents would survive. Second, erosion and metamorphism erase continents. Even though continental crust is more stable than oceanic crust, it is not invulnerable. Over hundreds of millions of years, mountain ranges rise and erode. Basins fill with sediment, then get uplifted and eroded again. Tectonic collisions subject rocks to heat and pressure, transforming sediments into metamorphic rocks and obliterating original textures and some chemical signals. Large portions of the continental rock record have been recycled this way. Third, the rock record is incomplete. Geologists estimate that only a small fraction of Earth's history is preserved in accessible rocks. Unconformities, gaps in the sedimentary record, are common. A civilization that existed during an interval poorly represented in the rock record might leave no accessible traces simply because the rocks from that time are rare or missing. Fourth, signals can be diluted, localized, or short-lived. If the civilization was small or its industrial phase brief, the signals might be weak and confined to specific regions. A localized metal enrichment in one sediment core might be dismissed as contamination or an analytical artifact. A single anomalous pollen assemblage might be attributed to local disturbance. Without replication across multiple sites, the signal would not be recognizable as global. Fifth, a civilization could be advanced, but low impact. Suppose the civilization developed renewable energy sources that did not require burning fossil fuels. Suppose they used advanced materials that did not fragment into microplastics or did not persist in the environment. Suppose their agricultural practices were sustainable and did not accelerate erosion. Such a civilization might leave only faint geochemical traces, difficult to distinguish from natural variability. Sixth, we might not be looking in the right places or at the right timescales. Geologists routinely study sediment cores and rock formations, but they are usually focused on reconstructing past climates, understanding extinction events, or exploring for resources. A geochemist analyzing carbon isotopes in a marine core is looking for climate signals, not evidence of ancient industrial activity. Unless someone specifically searches for the bundle of traces we have described, and searches in the right time intervals, the signal could be overlooked. Seventh, the signal might exist but be attributed to natural causes. Imagine a sediment layer with elevated metals, isotopic excursions, and charcoal spikes. If these anomalies appear near the time of a known large volcanic eruption or impact, geologists might reasonably attribute the signals to those natural events without considering alternative explanations. The burden of proof is high for extraordinary claims, and the default assumption is always to explain observations with known natural processes before invoking something unprecedented. Eighth, detection sensitivity matters. Some isotopes decay to levels below current measurement thresholds over millions of years. Some particles degrade to molecular fragments that require advanced analytical techniques to identify. If the technology to detect these traces is only now becoming available, earlier studies might have missed them. All of this adds up to a crucial point. Absence of evidence is not evidence of absence, but it does constrain scenarios. If an industrial civilization existed and operated at a scale and impact comparable to modern human civilization, and if it existed within the last few hundred million years in regions where sedimentary records are well preserved, we would expect to see the bundle of traces in at least some cores and formations. The fact that we do not suggests one of several possibilities. One, no such civilization existed. This is the default position and remains the most parsimonious explanation given current data. 2. Such a civilization existed but was smaller, shorter lived, or lower impact than modern humanity, leaving weaker signals that have not yet been recognized. 3. Such a civilization existed long enough ago, more than several hundred million years, that most of the evidence has been erased by tectonic recycling, erosion, and metamorphism. 4. Such a civilization existed, and the evidence is present in some cores or rock formations, but no one has yet conducted the specific analyses needed to recognize the bundle. Each possibility has different implications for how to search and what to expect. The key is that the question is testable. We can design search strategies, collect data, analyze it rigorously, and update our understanding based on what we find. The absence of evidence so far does not close the question. It refines it. It tells us that if a pre-human civilization existed, it either left a subtler trace than we have described, or it existed in time intervals or locations not yet thoroughly sampled, or we have not yet applied the right combination of analytical methods to detect it. But the possibility remains. We could find it. And that brings us to the practical question. How would we actually search? How to test this for real? A search strategy. Searching for evidence of a pre-human civilization is not a matter of speculation. It is a program of systematic data collection, analysis, and hypothesis testing. Here is what a real search strategy would look like. Start with the bundle of 5 rule. Do not search for one trace in isolation. Search for overlapping signals in the same narrow time window. Isotopic excursions in carbon, nitrogen, and sulfur. Technofossils or synthetic particles. Artificial radionuclides, if nuclear technology was used. Metal enrichments with diagnostic isotopic and elemental ratios. Sedimentation shifts paired with biosphere changes. If all 5 or even 3 or 4 appear together in the same thin layer replicated across multiple independent archives, the case becomes compelling. Where to look first? Prioritize stable cratons and long-lived sedimentary basins. These are regions where rocks spanning hundreds of millions of years are preserved with minimal disturbance. Examples include the cratonic interiors of Africa, Australia, North America, and Asia. Long-lived lake basins like the East African Rift Lakes or ancient lake beds now preserved in sedimentary formations offer high-resolution records. Anoxic marine basins are ideal. Environments with low oxygen preserve organic matter and fine particles exceptionally well. Black shales, sedimentary rocks rich in organic carbon deposited in anoxic conditions, are natural targets. Examples include the Cretaceous oceanic anoxic events, intervals where large parts of the ocean became oxygen depleted and organic-rich sediments accumulated. Cores from these formations could capture global signals. Deep-sea sediment cores with continuous deposition over tens of millions of years are critical. International ocean drilling programs have collected thousands of cores from the world's oceans. Many of these cores are archived and available for reanalysis. A systematic survey of cores covering different time intervals, analyzing them for the bundle of traces, would be a logical first step. High-resolution lake sequences offer another target. Lakes with varved sediments, annual layers, provide exceptional time resolution. Even in older lake sediments without varves, sedimentation rates are often high enough to resolve signals at centennial to millennial timescales. Cores from ancient lake basins preserved in continental interiors are prime candidates. What datasets matter? Global compilations of isotope data already exist for carbon, oxygen, nitrogen, and sulfur across geologic time. These databases are used for climate reconstruction. Re-examining them with a focus on anomalous excursions that do not match known natural events could identify candidate horizons. Metal concentration maps and databases exist from geochemical surveys for mineral exploration and environmental studies. Integrating these datasets to look for unusual element combinations and isotopic signatures in sediments could reveal patterns not previously connected. Microparticle surveys are less common but growing. Studies of microplastics in recent sediments provide a template. Extending similar methods, analyzing sediments for synthetic particles using microscopy and spectroscopy, could detect technofossils if they exist. Radionuclide measurements require advanced mass spectrometry. Accelerator mass spectrometry can detect long-lived isotopes at extremely low concentrations, targeting sediments from specific time intervals, particularly those already showing other anomalies, and searching for artificial radionuclides would be a decisive test. The search would proceed in phases. Phase 1. Screening. Use existing datasets to identify candidate time intervals and locations where multiple anomalies cluster. This is desk work, data mining, and synthesis. Phase 2. Targeted sampling. Collect new cores or resample archived cores from the candidate intervals. Conduct comprehensive analyses: isotopes, metals, microparticles, organic geochemistry, pollen, charcoal, sedimentation rates. Phase 3. Replication. If anomalies appear in one core, test cores from other basins and archives at the same time interval. Replication across sites is essential. Phase 4. Hypothesis testing. Compare the observed patterns against predictions for natural events, volcanism, impacts, methane releases, and against predictions for industrial activity. Use statistical methods to assess whether the bundle of signals is more consistent with one explanation than others. What would count as a decisive null result? If researchers analyzed cores covering multiple time intervals over the last 500 million years, from multiple ocean basins and continental regions, with sufficient analytical sensitivity and replication, and found no instances of the 5-trace bundle clustering in a single horizon that would constrain the hypothesis significantly, it would suggest that either no such civilization existed in the sampled intervals, or any civilization that did exist left an impact smaller than the detection threshold. However, a null result would not rule out the possibility entirely. It would push the question further back in time, to intervals less well preserved or towards smaller scale or lower impact civilizations. A positive result, on the other hand, finding the bundle replicated across sites with no plausible natural explanation, would be extraordinary. It would require rigorous verification, independent replication by multiple labs, and exhaustive testing of alternative hypotheses. But if it held up, it would transform our understanding of Earth's history and the nature of intelligence and civilization. The tools exist, the archives exist, the analytical methods exist. What is needed is a focused, systematic effort to apply them to this question. And the question is worth asking because it sharpens our understanding of preservation, planetary processes, and the long-term impacts of technological activity. If we conducted this search and found nothing, we would have learned something valuable, that Earth's rock record is sensitive enough to detect industrial-scale impacts, and none are present in the intervals we searched. If we found something, we would have answered one of the deepest questions humans can ask. Were we first? But even the search itself clarifies what it means to leave a trace in deep time, and what traces we ourselves are leaving right now. Ending. The takeaway. Plus. Final forward pull. Geology does not hide history. It compresses it into thin layers, chemical shifts, and particle distributions that can be read by those who know how to look. Every global event, every planetary scale change in chemistry or biology or sedimentation gets written into the rock record in some form. What we preserve is not monuments. It is the physics and chemistry of our impact. The traces we have examined, isotopic fingerprints, technofossils, radionuclides, pollutant geochemistry, and sedimentation shifts paired with biosphere changes, are not speculation. They are measurable signals that any industrial civilization operating at planetary scale would generate. Whether such a civilization existed before us is an open question. But it is not an unanswerable question. It is a testable hypothesis with a clear search strategy and specific criteria for confirmation or refutation. What makes this question powerful is not the possibility of finding ancient ruins hidden in a jungle. It is the realization that our own civilization, everything we build and burn and spread across the planet, will eventually become a thin layer in a sediment core. The microplastics, the isotopic shifts from fossil fuel combustion, the radionuclides from nuclear tests, the metal aerosols from industry, the sedimentation pulses from land clearing. All of it is being recorded right now in lakes, oceans, ice, and soils. Millions of years from now, if another intelligence examines Earth's rocks, our presence will not be marked by skyscrapers. It will be marked by a bundle of chemical and physical anomalies clustering in a horizon perhaps 10 centimeters thick. This reframing shifts the question. It is not whether we will be remembered. It is what kind of signature we leave. And it is whether we have the tools and the will to search for similar signatures from deep time. The archives are there. The methods are ready. The data could be collected. The question is whether anyone will look systematically, with the bundle principle in mind, across enough time intervals and sites to either find the signal or constrain its absence decisively. And here is the final question, the one that pulls forward. If you had to choose one archive, one location, one specific sedimentary formation or ocean basin or lake core, where would you look first to test whether we were the first civilization on Earth? What measurement would be most decisive, and why would that measurement, above all others, resolve the question in a way that could not be explained away? The answer to that question is where the search begins.